The magnitude of the NMR signal depends very much on the specific material under test. Here we compare two samples of monodispersed colloidal silica dispersions. One is a pure silicon dioxide, the other is an aluminum modified silica. Both dispersions had been extensively dialyzed against distilled deionized water. The final concentrations were similar at 42 weight% and 36 weight% respectively, and the particle sizes were the same, 18 nanometers according to the manufacturer's literature. T1 and T2 measurements were made as a function of dilution of the suspensions, but the data was plotted as relaxation rates are. First, the linearity in the plot confirms that the assumption regarding fast exchange between the surface and bulk water molecules applies, and also that there are no concentration-dependent secondary phenomena that would systematically alter the relaxation data, for example, particle aggregation. Second, it is obvious that the T1 and T2 relaxation times for the pure silica are very similar. The slope of R2 is only a little greater than that for R1. A completely different picture emerges with the aluminum modified silica. The presence of the aluminum on the silica surface has a dramatic effect. The T2 values are significantly smaller than the T1 values, such that R2 is much greater than R1. Silicas are used extensively in a wide variety of applications, and it is well recognized that they can contain iron, Fe, and aluminum, Al, as impurities. The example given here demonstrates that NMR can readily reveal the presence of such impurities. Natural aluminosilicate materials, such as clays, are also widely used. They have very diverse crystal chemistry that is critically dependent on the clay's prehistory, and it is well recognized that care must be taken when comparing data on clays from different sources. It is clear, though, that NMR can be used to compare and contrast such materials. This topic will be dealt with in much more detail in a future video.